is your dependent variable that use the concept of house prices, if you remember. That's sizes of rooms, maybe land square, perimeter, all of those factors contributes to the price of that house. Do you guys remember?
Yes.
All right. So now that is that is under supervised learning because you have features and you have your target variable. Now there's something called unsupervised learning where your model is just learning patterns. It does not have a target per se that it wants to predict or classify. So we call that unsupervised when there is no labeling. So they just give you a random set of data and tell you to find patterns in that data, right? To build a model to find patterns. And is commonly used in segmentation, like customer segmentation. These customers are more likely to do this than these other customers. So it's majorly used in clustering, k-means clustering. So when you see some regressor and classification problems, we are trying to classify or predict something based on some input features. We are trying to. Oh, am I going? Right. Let me. Okay, so okay, let me do something. Let me quickly change my audio device. All right, please, can you guys hear me?
Yes.
Okay, can you hear me? Is it clear? So I've been able to join on my laptop, so I'm leaving off. I'm turning off my phone now. All right, just kindly confirm that you can still hear me. Can you guys kindly confirm that you can still hear me?
Yes, I can see you.
Yes.
All right, lovely, lovely. Let me go ahead and share my screen. Sorry for postponing today's class. Today at work I've been hectic. Um, yeah. So you mentioned that the last class Israel used cargo. So if we did this intermediate machine learning, so I think we looked at what we do when we encounter missing values. We looked at categorical values. Sorry about that. So really quickly, can everyone tell me if Israel covered this? If you guys did intermediate machine learning in the last session?
No, we're still at introduction to machine learning.
Okay. All right. So where do you guys stop here? You said you did under 15 and over 15. Thanks for a round of applause. Did you guys get to Random Forest?
No.
Okay, so you stopped at the, or you did this underfitting and overfitting. You guys do this underfitting and
Yes, we did underfitting and overfitting.
right, that's it. So just a quick, um, were you guys able to run this model? I remember we were trying to run one. We're trying to run one. Were you guys able to run this model in the last class?
No.
Okay. Did anyone try running it in Kaggle? Like following along this Kaggle and try running it?
No.
Alright. So because time is going fast, I would choose the I would not be running a specific for this class. Or maybe later we can have like a good session on the platform or we just run one of these models. Right? But for today's class, I'll just explain because the um this camp is coming to an end and we want to at least cover as many traditional machine learning models as possible. We want you to understand the workflow. Then I think last next week is the last one. We'll just be running as much models as possible. But for now, I want to go back to first principle. I want you guys to understand why we are doing what we are doing. Okay. So I'll take it that Israel has explained the underfitting and overfitting. But just to take it again, when your model is overfitting, if you remember in the last class, my last class, I explained that training a machine learning model is analogous to students that you send to school, right? The students will go to class from let's use Unilag structure. You go to class for like 12 weeks, you have lecture periods to revise and write exams, right? So the students will go to class, they would have assessments, C, then we have final exam. So your students going to class and learning is called training, is equivalent to training in machine learning. Your students is training, right? That's equivalent. Then your students now writing the exam is now equivalent to testing your data, testing your model rather to see how it performs on the same data. So now when your student does very well in the training, so when you have C, all of that, and the training sets, like when the training is when you are going to class and learning, using reading textbooks, going to library, you are preparing yourself for the test, which is the exam. It's the same thing. So when you train your model on the trained data, since it has answers to all these questions, because it's seeing the features and seeing the answers to, so it's learning the patterns in them. Okay, what are the constraints? What are the patterns, the mathematical relationships between these two guys? It's learning it, it's learning it. So it will have a very high score because you can also see the answer. But when you now give the students in the exam, the score will not be that high. Or if he learns well, if he actually understood and is not cramming, students will still do well in the exam to a fairly good extent, right? To still be able to bag B or A in like conventions. But if that student was just cramming, then now this is new data, thinking like one of the powerhouses of posting news after exams, the model will be like that. We shout, hey, exam, it will feel it will be having poor scores on the test data. So in machine learning, when you have trained your model, we were using decision tree here. Yeah, we were using the decision tree regressor, right? So when you train your model, this is fitting the model. This is when you are training it. You fit your data on the training data set. That is when you are telling it, learn from this data that people. right? Identify patterns, learn from this data. So it's a do well. So when you're now predicting the data, when your data has a score that is too high on the training, but now has a score that is low on the validation, your model is not able to generate, not able to take those concepts that you are seeing with the way you had the questions and answers. It's not able to generalize it to this new test set. So we call that overfitting. Anytime you hear overfitting, just look at it as your model cramming. You didn't learn anything, you're just cramming. If you come and ask it, you will not get it. If you give it, you will not get it. That's called overfitting. Now, underfitting is when your model didn't learn very well, right? It doesn't understand at all, even the training data set. So your model is not complex enough to capture complex relationships between the input variables or the features and the target variable. That's when you have underfitting. Does this correlate with what Israel said in the last part? Yes, I'm not answering. Can you guys still hear me? I can't hear me.
Yes,
Yes,
I can hear you. Yes, I hear you.
all right. So I was asking that what I said, did you understand it? Does it correlate with what you just said in the last part?
Yes,
All right. So again, when you build a model, right, you want to evaluate that model. You want to see how good that model is performing. That's where we utilize this evaluation metrics. So if you are dealing with a regression problem is something dealing with numbers. If you are trying to calculate, predict temperature, predict house prices, predict exam scores, right? You are dealing with numbers. So that's a regression problem. So a regression problem evaluation metrics is different from a classification problem evaluation metrics. So in a regression problem, you have metrics like, yeah, you have metrics like the mean average error. You can have the mean squared error. You can have the root mean squared error. Those are evaluation metrics for regression problems because you are dealing with a number, right? But for classification now is when you are classifying something. So let's say you have some set of features. You want to classify if that's the target. Let's say you're trying to classify if something is dog or cat, right? Is this a dog or is this a cat? Is this a dog or is so it has different evaluation metrics. When you use all these in average errors, mean you use things like F1, recall, how to score, and in regression classification problems, you have F1, recall. How to score is a question. Alright, so let me quickly brush through this. Give me a sec. You guys are not responding most times. That's why I'm teaching. But I don't know where you guys thought that I'll be repeating things. If you know that I'm taking something that's already been done, call my attention to it that we can move. Because time is on our side. This is where I stopped
Okay.
last class. And for what do you want to say? Do you want to say you can't hear me?
I wanted to say that like your voice was breaking before, so like I could not really hear you.
Or is it clear now?
Yes, it's better now.
Right. So this was where we imported the decision tree regression. We remember we're trying to predict house prices based on a number of inputs or features. We're trying to predict the price of a house in Melbourne area. So now when you're defining the model, this random state lies here, which is the parameter of this decision tree regressor method. This random state is to ensure reproducibility. So if I run this with random state equals to 1, if you run it with random state equals to 1, if Taiwo runs it with random state equals to 1, if one runs, all of us get the same answer. So we know we're using random, but we're using a pseudo random figure so that this ensures reproducibility. We'll all get the same figure. So you can decide which random state. The most common one among machine learning practitioners is actually 42. I don't know why, but everybody just uses 42. But yeah, this one is to ensure reproducibility because if you don't specify a random state, what's the default? What should be 42 actually? If you don't specify a random state, you might be getting different answers. So if I'm using a random state of 1, let's say it's using a random state of 10, while it's using a random state of 30, getting different answers. But if you use the same figure, you get the same answer because they are all constrained within that same probability space. Okay, that's what they are contributing. Many machine learning models allow some randomness in model training. Specifying a number for random states ensure that you get the same results in each run and is considered good practice. You can use any number and model quality won't depend meaningfully on exactly what value you choose. So that's what you're saying. You can use any number, okay, but just so that you can have that reproducibility, be consistent with whatever number you use. If you're using 1, continue with 1. If you're using 7, continue with 7. All right. So in practice, you want to make predictions for nuances from the market. Okay. Right. So now we have trained the model, right? X is the training data. If you remember, all the input, the features, right? Y is the target variable. So if you look at X dot H, these are the inputs. The rooms, the price, how prices are affected by rooms, bathroom, land size, altitude, longitude, right? So you don't want to predict the corresponding prices given these input features. So that's why we do this normal model that predicts X dot H, right? And you know that H is just to return the first 5 rows of the data set. So now, what does this mean? You see that this 103,000, 1,035,000. Yeah, 1,035,000. That is for 1. So based on these input features, my prediction for the house price of this particular house, this one, is this 103,500. So 1,035,000. For this one, based on this input feature, it has more rooms, it has more bathrooms and everything. The price is a bit small. I'm predicting that the price of this should be around 1,165,000. And then same thing. That's so this one is the corresponding one for our third row. This one is for the fourth row, and this for the fifth row. So that's what it means. Because of time, I'm just explaining them on a high level. If you still have more time, I'll try and do something. So now after that, you want to validate your model. You want to see, compare, and test because some models will perform better than others. So if you want to, you guys should check out scikit-learn. Scikit-learn is what's it so small? Scikit-learn.org is the official documentation for machine learning models, right? Simple and efficient tool for predictive data analysis, accessible to everyone, built on NumPy, SciPy, Matplotlib, open source. Right. So first one, identify which category an object belongs to. Classification, image recognition, spam detection. algorithms, gradient boosting, nearest neighbors, random forest, logistic regression. Well, logistic and linear regression are different. That is something we can already. Then this is regression now, predicting a continuous value attribute associated with an object, like house prices, um, exam scores, some of the applications, and drug response, stock prices, house prices. Some algorithms use gradient boosting, nearest neighbors, random forest, ridge regression, and so on and so forth. Then we have clustering, which I mentioned that it comes under unsupervised learning. Right? And you have automatic grouping of similar objects into sets. So you are grouping objects based on the condition. Most of these objects classify or satisfy conditions. So imagine if you are grouping people based on countries, are grouping based on their countries. So everybody here is Nigeria, one group. Everybody here is um Spanish, one group. Everyone here is Italian, one group. So that is clustering. Then you have dimensionality reduction. We're not going into that for now. And have model selection. So the business of scikit-learn, if you want to learn about any of these processes, just click on it. I click on classification, supervised learning. That is what see first. Then you see all of this. I'm not be able to cover all of this because of time. So it has everything along with the associated code. Right? And done examples. Ordinary disquest, ridge regression, suppose vector machines. So any algorithm that you want to use basically for normal, conventional, traditional machine learning, just come to scikit-learn. So now we are dealing with what scikit-learn decision tree regressor. Can you see it? There it is. So if I click on it, decision tree it tells you it's class decision tree, and these are the parameters or the arguments which you can tweak your use case or to your liking, right? And it explains what each of these parameters does. Criterion, splitter, max test, meaning split. We can see criterion, splitter, max test, meaning split. And it already has that's good examples too. That's good examples. You see here they call it for SQL, this is a hypothetic diabetes data sets in SQL, scikit-learn. Then from there you have this crossbar score is for evaluating your model. And here they import the model from scikit-learn tree, import this trend tree regressor. Low diabetes, X, Y, X will be your input features, Y is your target rate. Then regressor, then instantiates the model, is random states of 0. And they check the score, crossbar score X. This is a very fast way of writing code. Oh yeah, that is the thing about documentation. Everything needs to understand better, but to have granular examples, to understand, whatever you are working on. You have to use docs. But it's a bad habit among developers, or which me myself have used a lot of times that we rather spend 7 hours debugging instead of 30 minutes of reading. So don't be like me, try and read docs more often. Rather than trying and failing and pulling your hair. Alright. So now that I've built that model, back to what we are doing on that Melbourne houses. Okay, before I continue here, I want you to know that in the data sciences workflow or in the machine learning workflow, model building takes just like 10% of your time. It's one of the fastest things that you will do. What to take majority of your time is data cleaning, data pre-processing, and data analysis, your EDA, your data cleaning, you talking with your stakeholder, your clients on what features you can draw, trying to understand what's the importance of each feature and feature engineering. That takes this model building, it doesn't take takes only like 10% of your time. And you can actually build a function and use multiple models at once. Then you now compare which one is doing better. So in a case, you might see that your random forest regressor is performing better than your your decision tree regressor. So you can see a case where your gradient boost regressor is performing better than your random forest regressor, right? So you just keep using all those models. You see the ones that works best. Which one gives you a higher? Which one is performing better based on your evaluation metrics? So now we build a model. How do we evaluate it? How do we use it? That's where we come to model validation. We want to evaluate almost every model you build, right? And the relevant measure of model quality is predictive accuracy. So we want that model's predictions to be close to the actual prediction, what actually happens. And so many people made a huge mistake when measuring predictive accuracy. They make predictions with their training data and compare those predictions to target values in the training data. Problem with this approach is how to solve it in a manner. So this error, right? Error is actual minus predicted. And that is how you get the MAE. That's why we have the evaluation metrics for version problems. It's MAE, MSC, RMSC. So when the lower your error, the better performing your model is. So I think I have a is a project I'm working on recently. I delete that driver. Okay, yeah. Apparently I didn't save that. I can't download it. So let me use this guy. Okay, I don't think I'm sharing this screen. Let me go and change the one share. Alright. So this is the project I was working on, predicting oil, gas, and water production rates from a well, from a conceptual oil field. I want to show that thing I was talking about. The model video. Okay. Right. So this was me trying with different. This is a regression problem because I was calculating production rates. It's a figure per day, daily production rates, right? And I was working in multi-happy regression. Just with that. What I want to highlight is that I have random forest, I have gradient boosting, I have extra trees, I have extra boost. Have you? And see, these are the evaluation metrics. You have the RMSE for the oil, for the gas, for the water. And you see that my RMSE is very bad. 1153. The goal of RMSE MAE, you want it to be as low as possible, as close to zero as possible, because error is predicted minus actual minus predicted. So let's say you are trying to predict tomato prices, and the price is 300. If your model predicted that the price is 250, the model is not too bad. The error is just 50. If you predicted that the tomato price would be 289 or 295, that is a very good model. It's doing well because the error is small. Unlike when you have large errors, like when your model probably predicted that tomato price is 1.5 when it's 250. You know that that is a erroneous model, like what I was having here. My best performing model was extra trees. But let me not use this example. Let me use guys will be seeing my something now, the same confidential data. Yeah, be as fast as possible. So this is what I was talking about. Now this was for another problem. But see that I just put USOs. I was working on a regression problem. I just put them in a function and I predicted them their MA and R2. So for your MAE, your MSC, your RMSC, you want the values to be as close to zero as possible. Right? So the difference between actual and predicted, they want it to be as close to zero as possible. But your R2, you want it to be as close to 100 as possible. So R2 is the only metric that you want to be high. So when you say, so this is like a R2, this is something like a model is 42% correct. When you say 0.42, it's like 42% good. That is accuracy level. So the error is like 22. An error can be as low as 22. Error is low depending on your use case, right? So if this is maybe calculating distances, 22 kilometer is large. Or if you are calculating prices, maybe $22 variation might be. So it's depending on what you are working on, right? So it's highly contextual. So here now you see that I just put models together. As now I measured it. So you see that from here, the best performing is gradient boosting. That 21, MA of 21, which is lower than the others. And that a higher R2 than the other, it has 45%. But this was the bad, so I decided to have it. But that's just what I wanted to show you. And this is just now view the model. Now I want to see what's the mean absolute error. So now from our predicted home prices, you see that the mean absolute, the MAE is 434. So that is not too bad since this is in house prices, right? So if a house is 150,000 and a predicted to cost 100,000, the error is 50,000. So yeah, this is 434, and we are working with houses that are in millions. Since this is 434 point something, I think this is very good. Consider this error now was 665,806. Right. So now when you see a model is doing very well on the training or doing poorly on the testing, you know that your model is perfecting. And when it's not doing very well on both of them, the training is doing bad. Right? You have to customize your model to be able to account for more complex relationships with your data. They just mute and speak. I just saw your hand.
Yeah, I have a question.
Go ahead.
What does that random space is equal to 0 or 1? Because I'm seeing 0 sometimes, I'm seeing 1 sometimes.
Yeah, so when you just random state is to ensure reproducibility so that your results will be consistent. When training, you enact a bit of randomness in training your data, but you want that random to be consistent. So if I have a random state of 1, everybody is using 1, you get the same result. If you write the exact same code, you get. But if I'm using 1 and someone is using 5, our results will be different. So specifying the figure is to ensure reproducibility, right? So that if you run this again after tuning your parameters, right? If you are trying to improve your model performance, customizing your models, if you now use another random state, you are just being redundant because you are looking at it in another you do random probabilistic space. There's a lot of English. But you're looking at it in another dimension. Just look at it as you're in another dimension. You are now measuring it based on another dimension guidelines. In summary, you're welcome. Always use, if you are using 1, stick with 1 throughout your project. If you are using 7, stick with 7 throughout your project. If you are using 42, stick with 42 throughout your project. So that it will ensure reproducibility. Does
Okay, thank
that
you.
answer your question? All right. So, so, so we use decision tree regress service. So now they want to show you using random forest. Right. So this is now an example using random forest. So you see with random forest, right, they instantiate a random forest regressor. You know, we're using decision tree regressor. And we're trying a random forest regressor. And we gave it the name forest model. We're saving it to this variable name that we named forest model. Right. So now we're now predicting these houses now. What is random forest? So now look at models like students. One student's learning patterns was different from another. So it's possible for one student to perform better in an exam than the other student. Same thing with models. One model can perform better than another model. And in another case, that model that performed worse might perform better than that one that's performing better than this before. So that's why it's good to experiment with different models to see which one is best performing, which one can correctly um, map your data or understand those patterns in your data. So now this random forest that is here now, if you remember, that one had 260 something thousand, if I'm correct. But this one is less. This one has 191,000. So this is performing better. There's likely room for further improvement, but this is a big improvement over the best decision tree error of 250,000. And their parameters are changed to, yeah, that's hyperparameter 2, which hopefully we'll look at in next week. Uptime parameters. So yeah, so now we looked at that. We touch on feature engineering. We touch on feature engineering.
No.
So to cut the long story short, because I want to touch this before we call it a wrap for today. Feature engineering is engineering features. So let's say you are giving data, right? You are giving data on um how do I put it? Feature engineering is creating features manually. You are engineering those features based on features that existed before. So eventually you are giving a data set that has let's say the data set has direction, distance, and then car prices, right? Or mileage. Mileage is like the amount of distance a car can cover under certain conditions, if I'm correct. But yeah, if you are giving distance, direction, and mileage, you can engineer a new feature called speed. And how will you do it? You merge speed. Speed is what? Distance times time. So you have distance, direction, which features did I mention before? You have distance, direction, and time, and you have mileage. Mileage is your target variable. You can engineer feature engineering a new feature called um speed, which is equal to what distance times time to give you a speed based on those features. So that is basically what feature engineering is. That is a very basic example. But you know, there's increased layer of complexity based on your use case. So if you are working with diabetes data sets, there's some features you have to talk. If you want to do some feature engineering, you have to talk with a domain expert to know, okay, what and what can I wrangle together to create another new feature that can actually affect my model performance. Because creating new features like that can help your model to capture relationships better and it leads to better model performance, which is good for you and good for the business. So that is the very quick high level summary of featuring. If you have questions, ask me. If you have questions, ask please. All right, so we looked at um we looked at intro to machine learning. What we gave was just a very high level of building models. You need to account for more things before you actually do that. During when we were having our session with pandas, we looked at how to handle missing values. Right? And missing values is one common problem or one common headache that data practitioners face because data is not complete. There's missing values. And when you are building a model, there must be no missing value. So you have to take an action on those data. Are you going to drop those data sets? Are you going to impute it with the median or mean? So you have to take an action before you go and build your machine learning models. Okay. So there are three main approaches to dealing with missing values. The first one is to drop them. So you see this one where there is man and 2.0. You just drop this column. So you just have 1. So you just have, can I highlight it? So they just drop this column. And dropping this, sorry, they drop this row. Dropping this row means that you use this data. Now, in this case, it's not bad. I'm just dropping one row out of 4. I still have 3, which my model can use that to learn and write the exam and still generalize and still perform it very well. Or imagine a case where you have a data set that has like 5,000 rows and 2,000 rows have missing values, right? And you know these are even just 2 columns. It might be that it's only 1 column that has missing values and the others have values. Will you not drop those 2,000? What of the data that is contained in all those other rows and in all those other columns? What's the data that is contained there? Right. So that's where we go to the better option, which is imputation. The imputation is filling those missing values with a number if you are working with a numerical data, or a placeholder text if you are working with textual data or categorical data. So for example, now we can fill this missing value with the mean as we are seeing here, right? Then this is an extension to imputation. This one is a better, and you get, and this usually leads to more accurate models. Imputation leads to more accurate models, and dropping that column because you are losing data. Another method which is employed is imputation, which is a standard approach and usually works well, but they might be systematically. In one word, imputation is like we now created a new data set to tell us that okay, we imputed we performed some sort of imputation in these places. So here now it's asking was bed missing? False, false, false. But yeah, bed was missing, so we put true. So this is sort of like telling our model the people we had to modify, right? Do you guys understand?
Yes.
All right, okay. So in that same Melbourne also data set, right? The model uses information such as number of rooms, bathroom, land size to predict home size. So we won't focus on the data loading, right? So, yeah. So we will drop columns with missing values. And if you remember from our Python, to look for columns with missing values, we use this is null.any. Do you remember? If there is no column with missing values, you return false. When we have missing values, we use this syntax. This function is what is doing is null.any or is null.sum. Let me see. If, can you see it? This is na.sum. We looked at it. We see that this column has 2,824 missing values. This one has 1,493. This one has 1,030. This one has none, none, none. So we looked at that. So here it was dropping columns with missing values. So this is this comprehension. I think we need our data structure. So column 4. So if x, what this is saying, what this line of code, what this block of code is saying is that if the column in the training data set, if there's any column that has null values, drop all rows that have null values in the training set. That's what this is doing. So if x dot trade is null, code for code in x dot train. So this is not dropping them. This is drop function. This is looking get the names of columns with missing values. Right. So if x dot train is null dot n, if they are missing values, return the names of those columns with missing values. That just brings them. And this way is now dropping them. Right. Drop columns with missing values. That's what this is doing. So you see this code with missing. It now drops them. And axis equals to 1. Remember, row is 0, column is 1. So at the column level, that's what this is saying. We drop columns with missing values at column level. So we drop all those columns. So now the MAE now, see that the MAE now is 1,800 and 183,000 from 250,000, 183,000. That's an improvement because MAE we are trying to reduce the score as much as possible to 0. Lower MAE is better, lower MSE is better, lower RMSE is better. So the approach 2 is now imputation, right? We are imputing. So using this simple imputer function, simple imputer, we're going to replace missing values with mean values along this column, right? So although filling in mean values generally performs quite well, this varies by data sets. So while statisticians have experimented with more complex ways to determine imputed values, such as regression imputation, these complex strategies typically give no additional benefits once you plug the results into sophisticated machine learning models. Let's see what happens here. So here we're imputing with the my imputer is simple imputer. So we imported, we instantiated the imputation here. So that PC PD the data frame, my imputer or simple imputer, then transform, just quick transform the X training data set for the valid. Right. So basically what's happening is that we're imputing with the this is the code to do so. And when we check the MA, you see that it's 178. It's not much difference from this one that was 183. Yes, it's lower, but not really much. But it performed better. So, but it doesn't really give much that stark change for optimization that we are looking for. We see the best approach. So from method 3, an extension simplification, right? So we're now adding, after doing that, so cause is missing, we add this plus was missing, just like we saw here, right? That the value was missing, or we have imputed a value here. So that's what we're doing here. But we are now dropping those. Then now we are now approaching. So we see that this one now is 183,550. It didn't perform as good as taking the wrong one. This one is 178,097, and I think this is the best performance. 178, 178. There's no much difference. 166, 97. It didn't perform as good as this one. Yeah, it's performed slightly worse than I can approach to. So why did imputation perform better than dropping the columns? Right. So for each column, less than half of the entries were missing. And dropping the columns removes a lot of useful information. So it makes sense that imputation will perform better. Now, it's just like when you are exposed to more examples to something, you perform better than when you are not exposed to examples to do something. What do I mean? If they are teaching you something and they teach you sparsely, you won't do as well as when you had a lot of resources to prepare and practice. It's the same thing with your modeling. The more data you get, the more data points that you have given your model to learn from, or it's now evaluate, it's now test it using the does predict method. Do you guys get the analogy? The more data sets you give your model, the better it performs. Do you guys understand?
Yes.
So that is why this guy is performing better because we didn't drop them. We just imputed a value here and it performed better than when we dropped this model because it had less data to learn from. So that is one problem we try and mitigate in machine learning. So that was looking at it from a numerical data types. There's a lot of non-numeric data types too that are used in machine learning. But I think this is where Israel will continue from the past. Categorical variables. How do you handle missing categorical variables? Categorical variables can either be nominal or ordinal. So we use one of the coding. I've barely used ordinal coding. The one that is majorly employed is one of the encoding. So they encode it, and there is not enough time to show that specifically. But hopefully, I'll relay this to you and we should start from the next class. The next class, next week, we'll look at building models as much as possible. Guys, any questions? Covered a lot. Anything I mentioned that is not particularly clear, I want to shed more light on.
No, I'm okay.
All right. Salamde, what about you? Salamde, are you okay too? Anything you want me to?
Yeah, I'm okay.
All right then. So see you guys in the next class. Have a lovely week.
You too. Thank you.